Okay, so today we're looking at intermolecular forces. The syllabus outcome for this one is explore the similarities and differences between the nature of intermolecular and intramolecular bonds and the strengths of the forces associated with each in order to explain the physical properties of elements and physical properties of compounds. So there's some, as usual, there are some revision questions at the top of page 91. So have a go at those. If you haven't done them, pause the video. If you have, let's go on to the answers. So the first thing, what involves the transfer of electrons, that's ionic bonds. Sharing of electrons are covalent bonds. Non-polar covalent bonds share the electrons approximately equally. And polar covalent bonds have the electrons shared unequally and therefore produce an electric field, which we call polarity. So we're looking at intermolecular forces today. So the bonds we've looked at in last lesson have been between atoms. So we call these intramolecular forces. So for those that know the difference between intra and intra and inter. Intra is within, inter is without. So that's why we can have the intranet, which is a facilities network, or we can have the internet, which is a bunch of networks network to each other. So the same is with these forces. So we've done intramolecular. We have to look at intermolecular forces. So these occur between molecules. Now they're responsible for many of the physical properties that we observe in matter. Now there's three main types. We firstly have the dispersion forces. We can also call them van der Waals forces or London forces. We also have dipole-dipole interactions. So that's the second one. And we have hydrogen bonds. Okay, so we'll go into what each of them is right now. So let's start with dispersion. So dispersion forces, also called London forces and van der Waals forces, they're small interactions of temporary electric fields created by electrons around an atom. Basically, we have electrons in orbitals. By chance, what could happen is all of the electrons build up on one side of the atom for a brief period of time. Okay, so we could get this partial positive, partial negative charge, within the atom or within the molecule. Sorry. And so we can get that. It's temporary, but it exists. Now, what happens when another molecule comes close to that one with the fluctuating dipole? The dipole induces one in the other molecule. So basically what happens is on the positive side of where we had that chance charge separation, that positive side will start to pull electrons towards that side of the second molecule. So what we do is we have the electrons go to this side first, and then because of these charges, all the electrons in this atom want to go that way as well. So they'll build up on that side. And the same thing would happen if we had a third one. We'd have the charges build up on that side. So the negative charges build up on that side and the positive on that side. And it's that process that helps keep atoms together. Sorry, molecules together. The dispersion forces depend on the number of atoms within a molecule. Basically, the more atoms, the more chance of this charge separation can occur. This leads to the trend of higher molecular mass producing stronger dispersion forces. And so that's the basic thing. So if there's nothing else within, no other effects within the molecule, as we increase the mass of the molecule, then the dispersion forces get stronger. Now, dipole-dipole interactions. These dipole-dipole interactions arise from the polarity created by polar covalent bonds. Now, each polar covalent bond creates what we call a dipole moment. Okay, so it's just a little area of differing electric field. Now, each dipole moment adds through space to create an overall dipole moment, and it's just using 3D vector addition for those that know what vectors are at this point. Now, if there is an overall dipole moment, then the molecule will undergo dipole-dipole interactions. So here we have an example of one that has those dipole-dipole interactions. So this is chloromethane. Basically what we've got here, we've got carbon in the center, some hydrogens around the outside at the bottom, and the chlorine at the top. Now between carbon and chlorine, chlorine's more electronegative, so it's going to have the partial negative. Between carbon and hydrogen, the carbon's actually going to be the partial negative. Okay, so we're going to get this sort of thing happening. So we're going to get the charge, the electronegativity is producing partial positives on the hydrogen, partial negative on the chlorine, and the carbon will probably stay about neutral because those positives and negatives kind of balance each other out. So what this does is it creates what we call a net dipole. So it's that overall dipole. If we have one that's very symmetrical, so symmetrical through 3D space, what can happen is all of the charges basically add towards this, to zero, basically. So in this one, we've got this methane molecule, and even though we get some polarity between the carbon-hydrogen bonds, because of the way they are pointing, they all kind of cancel each other out. Okay, so we get an overall zero dipole for that. So methane's not going to undergo dipole-dipole interactions, but your chloromethane is. Now here's just a little diagram of how it happens. So this is HF, so hydrofluoric acid, hydrogen fluoride, whichever you want to call it. So we can see that one side becomes electron rich, one side becomes electron poor. So this is our dipole. Now the negative side of that, so the fluorine side, is going to have a dipole-dipole interaction with the hydrogen from another molecule. And so these bonds are a lot stronger than the dispersion forces because they're permanent, they're not temporary. Okay, so they're always there. The last one we're going to look at is hydrogen bonding. Okay, this is a special type of dipole-dipole interaction that occurs in molecules that have hydrogen covalently bonded to oxygen, nitrogen, or fluorine. Now, basically the electronegativity of those three atoms combined with the presence of lone pairs of electrons on those atoms creates a very, very strong dipole moment. When this is brought near another that is the same, the intermolecular attraction becomes very strong. So here's some examples. So the first one is ammonia, so we've got an NH bond, so that's quite polar. Nitrogen also has a lone pair of electrons, which is, it's an electron-rich area, so it's going to be attracted to strongly delta positive areas. So we can see that here. So we can see that this partial positive is very strongly attracted to that partial negative. Okay. Same with between water, so we have this delta positive hydrogen being attracted to these lone pairs here. In hydrofluoric acid, this H plus and these electrons on this fluorine, they like to bond. We've also got an example of acetone here. So again, lone pairs, and we've got some hydrogen bonding from water. Okay, so this is why water and acetone like to mix. Here's just a little table of the strengths. And yeah, so all of the intermolecular forces we have looked at today involve electric field interactions. So some are temporary, some are permanent, and some are quite strong. So the dispersion forces, this applies to all molecules. The forces are only temporary, and so that's why they're so weak. So the strength is about 0.1 to 5 kilojoules per mole. Dipole-dipole interactions are only for polar molecules. Remember, it has to have that overall dipole. And it's a strength of between 5 and 20 kilojoules per mole. And lastly, hydrogen bonding. So those special three types of bonds, they can be up to 50 kilojoules per mole. So they can be actually quite strong. Now, if you think of water, water is it's a very light molecule. It only has an atomic mass of about um, 18. Okay, but it's liquid at room temperature. Now that's because of those hydrogen bonds. The hydrogen bonds keep it as a liquid, even though it's so light that normally you'd expect it to be a gas at room temperature. Now, the importance of the intermolecular forces. So we're learning about them, but what's important about them? Well, the intermolecular forces are the driver behind some of the physical properties of compounds, particularly melting and boiling point. We can observe the effect of intermolecular forces by looking at boiling points of different compounds and keeping as much similar while changing one of the aspects of it. Okay, so if we have a look at dispersion forces, we said dispersion force depends on molecular mass and it can't be a polar molecule. So we've had a look here. Here's some non-polar molecules. So F2, Cl2, Br2, and I2. Because they're just diatomic elements, each atom within the molecule has the same electronegativity. So there's equal sharing of those electrons. Basically, what happens, having a look at the molecular mass, as we increase the molecular mass, the boiling point increases as well. Okay, we're also increasing the number of electrons because that goes up with the mass. Now, accounting for everything else, which it should be pretty well controlled, we can see that massive effect on boiling point just from weight. Fluorine and chlorine, gases at room temperature, bromine's a liquid, iodine's a solid. Nice purple crystals. If you have a look at dipole-dipole interactions, so what I've included here is 5 elements that are approximately the same molecular mass. Okay, so they're all between 40 and 50, but they have much varying dipole moments. So overall, propane has a very low dipole moment, so there's not much dipole at all. And we can see the boiling point of 231 Kelvin. So that is actually, what's that, minus 42 Celsius. Okay. As we start increasing the dipole moment in dimethyl ether, so it's almost exactly the same molecular mass, but it increases to minus 25 degrees Celsius. Okay, so that's just by the introduction of an oxygen. Chloromethane, which has a molecular mass of 50 and a dipole moment of 1.9, has a very similar um, boiling point, so 249 Kelvin, so about minus 24 degrees Celsius. Okay. Acetaldehyde, so the dipole moment's jumping up by 0.8, and we can see that this one actually has a boiling point that's above zero now. It's about 21 degrees Celsius. And lastly, acetonitrile, which has a dipole moment of almost 4, and even though it's the lightest of all the molecules, it has the highest boiling point, okay, which is about 82 degrees Celsius. So you can see, even though our lightest one, even though acetonitrile is our lightest, it has our highest boiling point, and that's just because of that dipole moment. And now just having a bit of a look at hydrogen bonds. So dimethyl ether is a molecule where the oxygen is rather central and it's covalently bound to the 2 carbons. Ethanol, on the other hand, so I'll just draw dimethyl ether just so you get a bit of an idea for those that have any idea what I'm drawing. So we see that oxygen's central, there's no hydrogens attached to it. With ethanol, on the other hand, some of those atoms swap around and it gives us this kind of molecule. So we actually have an oxygen-hydrogen bond, which is what's required for hydrogen bonding. And so we can see with dimethyl ether, there's no hydrogen bonding, and it has that boiling point of 248 Kelvin, which was, I think it was about minus 28. Hold on, let me just double check. so minus 25 degrees Celsius. Now, just rearranging that molecule so that the oxygen's bonded to a hydrogen gives us hydrogen bonding, and it suddenly spikes our boiling point up to 78 degrees Celsius, okay, which is about 100 degrees higher than the dimethyl ether. Okay, so we can see that importance of hydrogen bonding. So, summary for today. So, intermolecular forces are forces acting in between molecules. Includes dispersion forces, or also called van der Waals or London forces. Includes dipole-dipole interactions and hydrogen bonds. Now, the strength dispersion is less strong than dipole-dipole, which is less than hydrogen bonds. And lastly, the intermolecular forces affect the physical properties.